Welcome to Brain Vision.
All right. We need to look at acetaldehyde or acetaldehyde, usually call it acetaldehyde, which is this structure. You could also draw it CH3, COH. The important thing is that we need to indicate hybridization and bond angles around the carbon and the oxygen atoms in acetaldehyde. So let's get started. As well as draw a 3D structure, so we can work on that. But let's look at the carbon atoms. First, we have a CH3. So CH3, the carbon also has a bond to another carbon, so that's 4 bonds. Carbon with 4 bonds is sp3 hybridized, and they are tetrahedral. Okay, so that should tell us the hybridization. What about the bond angles? If it's tetrahedral, then we're looking at 109.5 degrees. That's just comes out of the fact that it's tetrahedral. Now let's look at this carbon. This carbon has 1, 2, 3 bonds. One of them's a double bond, but it has 3 electron regions. Carbon with 3 electron regions is sp2 hybridized, and it is trigonal planar. That also tells us that the bond angles are like a peace sign, 120 degrees. Great. And we also need to look at the oxygen. Now, the oxygen has a couple lone pairs, and it too has 3 electron regions and is therefore as well sp2 and trigonal planar. And therefore, while the bond is linear because it has 1 bond, and these are just lone pairs, if we wanted to look at the angles between the lone pairs and the bond, it would also be 120 degrees. Now, if we want to draw a 3-dimensional structure of this, we can start from the carbon, double bound to the oxygen. This is planar, so it's in the plane of the page. This bond to a hydrogen is also therefore in the plane, and this bond to a carbon is also in the plane. Okay, now this carbon is sp3 tetrahedral, so we can put 2 bonds in the plane. One of its hydrogen bonds, and we've put the carbon-carbon bond in the plane. And if 2 bonds are in the plane, then that means we need 1 bond pointing up and 1 bond pointing down. So we've got a hydrogen pointing at us and a hydrogen pointing away from us. These are 109.5 degrees. Okay, now we've got to look at ethanolamine, I guess I would call it. Great. So we've got a CH2, CH2, and then NH2 here, and this is an OH on the end. Okay, so it's a 2-carbon chain with an OH on one side and an NH2 on the other. Right. So let's start with the oxygen. This oxygen has 2 lone pairs, therefore it's got 4 regions, 4 electron regions. It's sp3 hybridized, which means 109.5 degree bond angles. This carbon has 2 hydrogen bonds, or 2 hydrogens bound to it, 2 hydrogens here. So this is also 4 bonds, that's sp3. This carbon, same deal, sp3. And just like the oxygen, that means 109.5. And this NH2 also has a lone pair. That's 3 bonds and a lone pair, 4 electron regions. Everything in this molecule is sp3 hybridized, and all of it will have 109.5 degree bond angles. All right. Now we can try drawing a 3-dimensional structure here. So let's start with this oxygen. Let's say it's got a bond to hydrogen in the plane and a bond to carbon in the plane, which means its remaining 2 bonds need to be coming up towards us and away from us. Now this carbon here, we can put 1 bond in the plane, and the remaining 2 bonds will be coming up towards us, away from us. This carbon 2 will put its bond to nitrogen in the plane, So it's got 2 bonds in the plane, one coming towards us, one going away from us. And this nitrogen, let's put 1 bond to hydrogen in the plane. And then we've got a hydrogen remaining. Technically, like, we'd have a lone pair either going down or towards us, but we don't typically draw lone pairs with wedges or dashes. In fact, we don't usually include them at all in 3-dimensional drawing, so this would suffice right here. This would be a 3-dimensional drawing. All bonds are 109.5 degrees because everything is sp3 hybridized.